Welcome to week 3 lecture 3. In this lecture we will discuss primality testing. Now in our discussions of RSA algorithm we found that one of the most important thing in setting up an RSA crypto system is that we have to have large primes, and these primes have to be about 600 bits long. The question that occurs to us that how are we going to find out such large primes, and that is what we are going to discuss today. So, we will be discussing algorithms which decide whether a prime is whether a number is prime or not, and these algorithms are called primality testing algorithms. One point of caution here is that these algorithms are not deterministic algorithms. So, the result of these algorithms are not correct always. What happens essentially is that suppose we have a primality testing algorithm which is not deterministic. We will be discussing these algorithms soon. These algorithms are, if we take a number, a positive odd integer, we apply the algorithm on it, then the algorithm will return the input is prime or the input is composite. These algorithms are constructed in such a way, if n is prime, it will determine n is prime without error, but there are cases where it may decide that n is prime although the input is not prime. In that case it will have error. Then after designing such an algorithm, people compute the error probabilities of these algorithms, and they found that the error probabilities are bounded. That is to say that if they found that the error probabilities are bounded and the bound is reasonable, then we know that we can work with these algorithms. We will look at these things a little later, but first we look at our first algorithm. This is called Miller and Rabin algorithm. Now before going into Miller and Rabin algorithm, we will discuss something that we have already done before, that we have defined phi m, where m is a positive integer, and we have said that phi m is the number of positive integers co-prime to m and less than m. Now if we also know that if we take any integer a and then if we take a raised to the power phi m, then this is congruent to 1 mod m. This is something that we have proved in our previous lecture. Now suppose m is prime, then phi m is equal to m minus 1. This is because that any integer less than m and of course greater than or equal to 1 is co-prime to m, since m is prime. So let us change m to p. So here we write this, so it looks more like prime. But if we apply this result here, then we know that if I take any element A in Z, then A raised to the power p minus 1, which is equal to A raised to the power phi p, is going to be congruent to 1 mod p. Now, we question that what happens if we run it the other way around. Now, suppose we take a number p, number n, let us say n, we want to determine whether n is prime or not. First of all, if n is even, then there is no point checking it, because we know that an even number cannot be a prime. So, n has to be positive odd. And now, what we do is choose an A which is inside Z, and then take A raised to the power n minus 1 and ask whether this is equal to 1 mod n. Now, it may or may not be 1 mod n. If n is prime, of course, it is going to be 1 mod n, but otherwise also it may be 1 mod n. What we do in this algorithm, if it is 1 mod n, we say that it is a prime, but if it is not 1 mod n, we know for definite that n is not prime, and this is the strategy. And now let us look at the slide. Here it is Miller-Rabin algorithm. In this algorithm, we have made some small changes to make the algorithm work better. So, I have the input n, and of course it is odd, and now after that I am reducing n by 1, and then I am taking the factor of 2. So, I know that if n minus 1 is an odd is an even integer, so I factor it by 2 to the power k maximum for maximum k. So, it gets split up into 2 to the power k into m, where m is odd. Now, I choose at random an A between 1 and n minus 1, and after that I raise A to the power m mod n and store it in B. Now, I check whether B is 1 mod n. If it is 1 mod n, I say that n is prime. Well, I may be wrong, but I say that m is prime. Otherwise, I go into a loop. I basically keep on multiplying 2 with m one after another up to 2 to the power k, or in this case 2 to the power k minus 1, and check whether A raised to the power 2 to the power I into m is equal to 1 mod is equal to minus 1 mod n. That is what we do in this step. If you look at this step carefully, you will find that is exactly what is happening. If we find that at any iteration of this loop B is congruent to minus 1 mod n, we say that n is prime, otherwise we return n is composite. If we look carefully, we will see that we are essentially using a kind of idea that we discussed here in a little refined manner, and it will give me well an idea whether n is prime or not. Now, what is interesting here is that this algorithm has a very nice error bound of error probability bound, and that bound is 1/4. We know that probability of error of the Miller and Rabin algorithm is at most 1/4. So, therefore, if we run Miller and Rabin algorithm, let us say 50 times, then the probability that each time this algorithm is giving me a wrong answer is 1 by 4 to the power 50, which is equal to 1 by 2 to the power 100. So, the probability that it is giving me correct answer is 1 minus 1 by 2 to the power 100, which is very large. So, this is an algorithm that can be used in practice to determine whether a large positive odd integer is prime or not. There is another algorithm which does the same thing and which is also commonly used, and that algorithm is called Solve-Strassen algorithm. But before we go into that algorithm, we have to learn a little more number theory. We come to a topic in number theory which is called quadratic residues. So, we will discuss that. Suppose p is an odd integer, suppose p is an odd prime and a is an integer. A is defined to be a quadratic residue mod p if a is not congruent to 0 mod p and the congruence equation y square congruent to a mod p has a solution in z sub p. A is defined to be a quadratic non-residue mod p if a is not congruent to 0 mod p and a is not a quadratic residue modulo p. Now, let us look at some example to check which numbers are quadratic residue mod p and which are not by fixing a p. We fix p to be 13. So, we have p equal to 13, of course, it is an odd prime, and we consider z13 which are numbers from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So, we have here z13, and then what we do is that we take the squares of all the numbers and we leave aside 0 because we are not concerned with 0. So, if we take the squares and take modulo 13, then we will get a set like this, or I should rather say sequence, because we will have repetitions. So, we will have a sequence like this 1 4, because 1 square is 1, 2 square is 4, 3 square is 9, then we have got 16, but 16 modulo 13 gives me 3. So, I have come up to 4, 5 square is 25 and 25 modulo 13 gives me 12, 6 square is 36, 36 modulo 13 gives me 10 because 13 2s are 26, then 7 also will give me 10, and then 8 square mod 13 will give me 12, 9 square mod 13 will give me 3, and similarly I will have for others 9, 4 and eventually 12 square mod 13 will give me 1. So, I have got the set of quadratic residues which are 1, 3, 4, 9, 10 and 12. So, inside Z sub 13 these are quadratic residues, and the rest are quadratic non-residues apart from 0. We do not say anything about 0. Rest namely 2, 5, 6, 7, 8, 11. these are also elements of Z13. Now we have a famous criterion, it is called Euler's criterion, which says that in order to determine whether a number is quadratic residue or not, take it to the power p minus 1 divided by 2 and take modulo p, that is reduce it modulo p. If it is 1, then it is a quadratic residue. If it is not 1, then it is not a quadratic residue, then it is not a quadratic residue. So, let us look at that. For example, if I start with 3, my prime is p, I take 3. So, 13 minus 1 divided by 2, which is equal to 13, and this is 12 by 2, this is equal to 6, 3 raised to the power 6. So, this is 27 into 27, and if I reduce modulo 13, this one, this is congruent to 27 mod 13 into 27 mod 13, which is 1 into 1, so it is 1. So, I can say that 3 raised to the power 13 minus 1 by 2 is congruent to 1 mod 13, and therefore, by Euler's criterion this is a quadratic residue. If you check another number from the other side, a quadratic non-residue, and do the same thing, then you will see that you are getting minus 1 mod 13 and not 1 mod 13, and it is not a quadratic residue. So, ultimately we land up into a very famous symbol which is called Legendre symbol. If we have an odd prime p and take any integer a by p enclosed in parenthesis is said to be Legendre symbol, and it is 0 if a is congruent to 0 mod p, it is 1 if a is a quadratic residue mod p, it is minus 1 if it is a quadratic non-residue mod p. Now, we have a generalization of Legendre symbol, and it is called Jacobi symbol, and Jacobi symbol can be used for n's which are not primes or odd primes, but we take any odd integer n. So, let us see how we define Jacobi symbol. So, if n is an odd positive integer and the prime power factorization of n is equal to product of I going from 1 to n pi raised to the power ei, then the Jacobi symbol a by n is defined to be a by n is equal to product of the individual Legendre symbols of corresponding to pi's with respect to a raised to the power ei, which is written over here. This is a Jacobi symbol. So, if you would like to calculate Jacobi symbol for a particular pair, let us come to the next slide. Here we have n, which is 175. It is an odd positive integer, and it factorizes as 5 square into 3. I am sorry, 5 square into 7. So, that gives me 175, and let us take a equal to 12. We would like to calculate the Jacobi symbol of a by n. So, it is 12 by 175, and then according to our definition let us look at the definition quickly, that we have factorized this, and then the Jacobi symbol is product of the Legendre symbols. So, we do this thing. So, we know that we have got 5 square. So, we write 12 by 5 whole square and then 12 by 7. Now, it is not difficult to see that the Legendre symbol value with respect to or modulo p of m will be same as the Legendre symbol value of m reduced mod p reduced mod p. So, what we do over here is that we take 12 and we have 5, we have to calculate the Legendre symbol with respect to modulo 5. So, what I wanted to say is that if we reduce 12 modulo 5, we get 7. The Legendre symbol value of 12 mod 5 and 7 mod 5 both are going to be same. No, I am making a mistake here. If I reduce 12 mod 5, that I will get 2. What I want to say is that the Legendre symbol value of 2 mod 5, 2 modulo 5 and 12 modulo 5 are same. This is not difficult to see. So, suppose I want to calculate the Legendre symbol value of this. It will be same as A mod p by p. That is what we are using over here. So, I reduce it to 2 5 whole square and 5 7, and now we can directly calculate the Legendre symbols by using the Euler's criterion. If we do that, we will see both are -1, and then if we calculate the product, then I will get -1. So, we have got the value of Jacobi symbol. Now, the problem of this method of computation is that it requires factorization of n, and which is going to be difficult if n is a large number. In the next lecture, we will discuss how to calculate Jacobi symbol when n is a large number without factorization by using certain properties of Jacobi symbol, and that will lead us to the Solves-Strassen algorithm for primality testing. So, this is the end of lecture 3.